Hello, my name is Jason Vance, and I'll be doing a presentation here on the role of quantum mechanics, in particular quantum tunneling, in the process of nuclear fusion. And I kind of wanted to preface this talk as a means of showing that quantum mechanics isn't something that's weird or only applies on very small scales or in areas that don't affect you very frequently. It's actually an integral part of our own existence here in the universe, and that it isn't quantum mechanics and special relativity and such that have the paradoxes, but actually classical mechanics has the inconsistencies. And hopefully, we'll be able to see some of that and go on forward, and I can give everyone a new appreciation for why we need quantum mechanics. So first, let's just start out and make sure everyone's on the same page here and knows what's going on. So what exactly is fusion? Fusion's when two nucleons come together and form a heavier nucleus. So in our case, we're going to be dealing exclusively with protons in this. So we're going to have proton-proton fusion. That's the main thing that happens in the sun, and we'll see some interesting examples of that later. So why doesn't fusion happen all the time everywhere? Well, there's two forces that are vying for balance. On an infinite scale, the electromagnetic force is predominant. It's the one that affects charges, so positive like charges repel each other, opposite charges attract, and it's mediated by the photon. Whereas the strong nuclear force has a very, very small range of about 2.5 femtometers or Fermis. Fermi and femtometer are the same thing, so if you hear me say one or the other, that's what they mean. Um, and it is about 167 times stronger than the electromagnetic force at that range, so it definitely takes over quite quickly. This is a nice graphic from the University of Chicago that kind of gives a little bit of a spiel about the two. I won't go into it too much because we're going to try and focus this on quantum mechanics. I just wanted to make sure everyone knew the two forces that are at work here and why we're using them. So we can represent these two forces as potential energy functions as a function of distance from, in our case, a proton. So what we're going to be considering here is a proton is the center of this axis. So we are saying there is a hydrogen or proton at the zero axis. This represents a proton. And what we're going to be considering is another proton coming in and attempting to fusion with it. So from our potential energy function that we've learned in intro E&M and stuff, we know that the potential energy of like charges will repel each other by 1 over r. So we've got this nice falling down 1 over r relationship here for our Coulomb potential energy. And then when I was looking into it, I was expecting there to be a similar formula for the strong force or strong potential energy function. But actually, there's only really three predominantly used approximations. The Yucca potential energy and Wood-Saxton potential, in particular, are used primarily for shell models, whereas the Reed potential is well, it's basically from experimental data that they've gathered, and then they've put this best fit line. So that's kind of why this function looks a little strange. It's a best fit function from data. And we're going to be going with the Reed potential because it's our current best estimate as to the actual potential energy. These have problems at zero, for example, like the Yucca potential and Wood-Saxton both say that this gap should be at zero, so all of the protons end up on top of each other. So this gives some spacing of about the width of one proton so that they don't overlap. So this is what we're going to go with. All of these graphs that you'll see have been set up so that they have the distance from the proton to the other proton in femtometers or Fermis. So all of the x-axis, I know this one's not labeled, but this is in femtometers. And the y-axis is going to be potential energy in mega electron volts, so MeV. So we get here, and in order to find our energy function or our energy well, we simply need to combine the two factors. And I have here solved for the factors that go in. The 0.7 was recommended to best fit the data, so that's what we plugged in for mu. X is just the distance from one hydrogen to the other. And this 1.439960 value looks a bit strange. It doesn't look anything like our original potential energy function for the Coulomb potential. This whole term is the Coulomb potential. But if you go back, you'll see all of those are constants. So this is just what happens when you end up converting 4 units of femtometers and MeV. I was actually a little surprised it turned out to be such a nice number, but that's what we've got for our potential energy well. And we can look at some features of this well now that we've got all of the energy understood and how to use this well, because this is a very powerful tool in the kit of anyone who does quantum mechanics or really any sort of energy related problem in physics. Like we'll see how to apply this classically even at the start, so we can see where the paradox comes about. But so what we can tell here is we've got a peak here at about 0.2 and some change mega electron volts. And then a giant well, so this goes way down to negative, I think 100 MeV from the previous graph. But outside of this range right here, it's basically looks exactly identical to our Coulomb potential graph. So it's Coulomb potential until the strong nuclear force overpowers the Coulomb potential, and there's a big drop here. So for fusion to happen, we need our other hydrogen to make it into this well. If the other particle can't get here, no fusion happens, and it's just repelled. So let's attempt to use what we've just constructed to calculate the classical critical ignition temperature of this of hydrogen. Basically, we're trying to figure out how much energy, or how much temperature in this case. We're going to convert energy into temperature and see what kind of values we get for what we believe would be required for fusion to occur. So we take the peak of that graph before. It was about 0.2. In this case, 0.206 MeV was the peak of that graph, and kinetic energy would be required at minimum, classically, to overcome the Coulomb barrier. So we can plug that value into our relativistic kinetic energy formula. It probably isn't required to use this, but I just was on the safe side because it is pretty fast. So it turns out to be going 6.3 million meters per second. And then using the three-dimensional thermal velocity equation, we get that the temperature of this is supposed to be about 1.6 billion Kelvin, which sounds pretty high. And if we compare it to actual results that have been measured for the core temperature of the sun, it's should be closer to 15 million Kelvin. So we're off by 2 orders of magnitude, which is pretty significant. And even more surprising is our conclusion here is that the sun shouldn't be burning. It doesn't have enough energy. There's not enough pressure or temperature inside the core of our sun to facilitate fusion. So there must be something else going on, because we can very clearly tell that the sun is indeed burning, and we have very good evidence that it has been burning for quite some time and is not likely to stop anytime soon. So there must be something wrong with our classical calculation in some way, or our classical understanding of physics. And the big spoiler for this, which you probably got from the title, was quantum tunneling plays a very, very big role in nuclear fusion. So what exactly is quantum tunneling, and what does it mean to quantum tunnel? In quantum mechanics, if a particle encounters a potential energy barrier, which a potential energy barrier could be, in our case, it's the electrostatic repulsion of the Coulomb force, and on the other side of the barrier, there's the strong nuclear interaction. So we've got, in our case, we have a little well and then free space outside. But in this simple example here, we've got some particle coming in, it's got some wave function, it encounters a barrier, and then in the barrier width, it's determined by an exponential decaying function. And you get this function by solving the wave equation down here. So let's look at the variables we have in this thing. We've got the mass of the particle, that's constant, don't have to worry about that too much. We've got the position, and we've got the energy difference of the particle and the potential energy. And inside of this well, or inside of the classically forbidden region, the potential energy is actually going to be higher than our particle's energy. And that's what leads to the exponentially decaying function when you solve this differential equation. So out here we've got, and this is going to be proportional to our probability of tunneling, which is over here from our physics textbook. So inside of here, we've got the term of mass, which was just our constant that we kept, so that's good. There's the 2m. It survived as expected. And we've got the potential energy minus the energy, and that's to be expected because the potential energy is actually higher than our energy. And we've still got our h bar squared constant, so that's good. And all of that's just going to be dependent on the width of this barrier. So the two things that really affect quantum tunneling's probability is going to be the width of the barrier and the height of the barrier from the energy of the particle. Because like if this energy was lower, the particle would just be over the barrier. This wouldn't be doing anything effectively. So what does it kind of mean to quantum tunnel, right? Like, is this thing busting through the barrier? And actually, no. It's just sort of teleporting from one side to the other. The energy is not affected at all. It's like you might look at this graph and think like, wow, that amplitude's way smaller. The energy must have decreased by a ton. But this is actually correlating to probability. So if you square this wave, it'll give you the probability of finding the particle here versus over here. The energy is actually based on the wavelength, and that doesn't change at all once it comes out of the barrier. Like clearly inside of the barrier itself, it has no wavelength, so it's hard to tell what's really going on here. But when it comes out the other side, the wavelength hasn't changed, so we're assuming that within this barrier too, it probably had the same energy as well. So how does this play into the potential energy graph that we made before that I said was so important? Well, you remember the well where the strong nuclear force was dominant, right as it comes over the Coulomb potential. It looks kind of like this. And because this is a finite width and has a finite height, there is a chance that a particle can tunnel through this barrier. And that's the main process that causes nuclear fusion. So before we go back to our sun example, let's take this kind of weird concept and play with it a little bit using our same model to try to confirm something that we already expect and can easily observe here on Earth. Because there could be some skepticism over the temperature of the sun, right? We want to make sure, and we just want to make sure our model makes sense for what we're doing. It's always good to test your model. So what we're going to do here is we're going to take some diatomic hydrogen, that's just a hydrogen bonded to another hydrogen, sharing electrons. And so they will be about 74,000 femtometers apart. And I got that courtesy of a chemistry textbook. I am not a huge chemistry buff, so I had to look this one up. But this would put our lower potential energy at 0 for 74,000 femtometers because these things are in stable stable orbit as diatomic hydrogen. They want to stay 74,000 femtometers apart from each other. So in order to simplify this problem down considerably and not have to deal with a three-body problem and a lot of things, all I'm going to do is I'm going to lower the potential energy at 74,000 femtometers to 0, and then check what the width of our barrier is and the average height of the barrier, and use that to calculate our probability of tunneling. And before we even do any calculations, what we're expecting out of this is basically 0, because we don't observe fusion just randomly happening. Like, your cup of water doesn't randomly explode thermonuclearly, so we're expecting this value to be very close to 0 or a negligible amount. And we'll talk a little bit more about a negligible amount after we do some of this calculation. So what is the potential energy at 74,000 femtometers? I went to my graph, I punched in 74,000 femtometers, and I found it's got about 19 electron volts worth of energy. So I subtracted 19 electron volts from my graph, but to put the potential energy at 0. And then I gave this this particle some kinetic energy of room temperature, which turns out to be from our same equations before. I actually used the relativistic one, which was definitely not necessary here at 1,754 meters per second, but it gives us an energy of about 0.16 electron volts. So that gives us a barrier width of course, 74,000 femtometers. That's how far we're apart. Technically, I probably should have subtracted 3 from this because there is the potential well, but it's fine. It's not going to make a huge impact. And to calculate our average barrier height, what I did was I integrated the function from the 3.5, from 3.5 to 74,000 femtometers, and then divided by 1 over 74,000 minus 3.5, and that gave us our average height in MeV. So now we've got a big square potential barrier that is 0.00187999 MeV high, and we're going to see what it takes to tunnel through that. And if we plug all these values in, because these are all the values we need, we've got the width and we've got the height, everything else is constant, so we plug that in, and it turns out, oh, we also have our energy, that one's important too. So after we plug that through, it turns out that a room temperature particle, 295 Kelvin, has roughly 0.3 times 10 to the minus 193 probability of tunneling. And to put this, big numbers like these are kind of hard to imagine or to contemplate. So, and some people might say like, well, that's not 0. We've proved our value wrong. For all intents and purposes, this is 0. So a nice thing to know is 10 to the 120 is the number of atoms in the universe. And we're several zeros beyond that for being closer to 0, because this is 1 over 10 to the 193. So this confirms our original assumption. You know, we expected to go into this and get a value very close to 0, and we did. So that's good. Our model holds up to our first test. So let's go on and let's try to tackle the sun problem again. So now we're returning to the sun problem with quantum tunneling. So this is going to be the same problem we did originally classically, and the same procedure we just did for diatomic hydrogen. Only there won't be a subtracted constant because this is just one proton approaching another proton, so we don't have to worry about subtracting any small amount for potential energy. And we're going to be starting with the NASA reported 15 million Kelvin for our core temperature, which gets us a velocity of 612,000 meters per second, which is considerably smaller than our original assumption classically. And if we punch that into if we take that energy, or we calculate the kinetic energy, we get 1,938 electron volts. So we need to figure out where that is on our graph to find out the first classically forbidden zone for our particle. And if we go down to our y-axis and we find 1,938 electron volts, it turns out it's about 743 femtometers away. So our barrier is going to be from this point down here at 743 femtometers to about 3.5 femtometers is where the strong nuclear force completely overpowers the Coulomb potential. So integrating this function from 3.5 to 743, and then dividing by the distance of this, we get an average barrier height of 0.0189 MeV. And so now we've got the barrier width, the energy of our particle here, and we've got our barrier height, the energy of our particle, and our barrier width. So we've got all the components we need to calculate the probability of tunneling. And when we do that, we end up with a value of 0.5 times 10 to the minus 18. And this sounds like a really, really small number. So let's think about it for a second and ask the important question that you should ask in every physics problem: does this answer make any sense? And on the surface, you might say no, but let's first just think about the bounds. Like, obviously, we can't have any value that's greater than 1 or less than 0 because that would clearly indicate some sort of math mistake. We've got a probability, so it has to be between 1 and 0. But let's think of what a really high probability would mean. If this probability was 1, it would mean all of the atoms inside of the sun would instantaneously undergo fusion reactions and explode. So we would have a bomb. And the higher this number is, the more of a bomb we have. What we really want is a slow burn, because this star's been around for billions of years and will probably continue to be around for billions of years, hopefully. So we are looking for a small number. And you might think, well, how could this possibly explain the amount of fusion that's happening in the sun? Because look at it. Well, the answer kind of lies in there is a lot of sun. So there is 10 to the 57 hydrogen in the sun. And if we multiply that by our probability of tunneling, we end up with a value of 5 times 10 to the 38 expected events. And for comparison, the sun is estimated to be putting out 3.7 times 10 to the 38 events per second. Now, we don't have any time dependence in ours, so the fact that these values are so close is more of a coincidence than anything else, but it at least shows us that we're on the right track. We're making a prediction that fusion should occur, and it's in the right order of magnitude in that the sun isn't instantly exploding, it's using up a small amount. Now we get to the part that interests me personally the most and was actually my original idea for a project here that ended up getting extended into fusion with the sun, as I found the Forbes article very interesting in quantum mechanics basically being the source of energy from our sun. But the thing that I find really interesting is actually muon catalyzed fusion, or cold fusion as it was dubbed back in the 1950s. And I'm sure you've all heard of sci-fi shows talking about cold fusion and the perfect energy source, but what does it really mean? So cold fusion would be, in a sense, fusion at any temperature or fusion at room temperature. So you don't need to heat it. So like we saw before, our diatomic hydrogen, without a heat source, had basically zero chance of fusioning, whereas the sun had a pretty reasonable chance of fusioning. And in muon catalyzed fusion, it turns out the temperature doesn't actually really matter that much. So we'll take a look at that with our same model here, but first let's do a little bit of background. So what is a muon? A muon is basically identical to an electron in every way, except it's 207 times heavier. It's got 207 times more mass. So how are these muons produced? They come from a pion decay. So a pion is two quarks that are linked by a gluon, and when they undergo the weak fort or undergo weak interaction, they can decay into a muon and a muon neutrino. And this over here is a Feynman diagram. They have axis of space and time. So it's important to figure out which one is space and which one is time first before you try and read it, because it doesn't seem to be consistent for how people set this up. But in this case, our time axis is along x and our space axis is along the y here. So we can see our pion here, which is an anti-up quark and a down quark. They undergo the weak interaction with the mediated by a W boson and then split off into our muon and our muon neutrino. Muons have a pretty short lifespan of about 2.2 microseconds, and then they decay back into a regular old electron. But during that 2.2 microseconds, they actually have some pretty interesting effects, and they can form muonic hydrogen, so they can bind into an orbit with a hydrogen, just like a regular electron can. They can do all the same things that a regular electron can while they're still around. So what does muonic hydrogen look like? And I thought this would be really interesting at first and was one of my ideas for a project, and then I realized the only thing it differs by is mass. And mass is a constant, and we saw in our last differential equation, constant doesn't do anything other than multiply your end result by a value. So muonic hydrogen looks exactly the same as regular hydrogen's wave function, but it's 1/207th scale. So you just divide your normal hydrogen wave function by 207, and there's your result. So how do muons catalyze fusion reactions? And when we looked at our potential barrier before, there were two things that affected your chance of tunneling, and in our case, the chance of fusion, because we're tunneling to cause fusion to happen. That was the width of the barrier and the height of the barrier. So you can get more energy if you pump more energy into a particle. You can attempt to go over the barrier or get a higher probability by reducing the distance between the top of the barrier. Or you could make the particles closer together. And muonic hydrogen is 1/207th the size. So if this binds to another hydrogen, they're now 207 times closer than they would normally be in diatomic hydrogen. So we can start out here, and we use the 74,000 femtometers that we had for separation for diatomic hydrogen that we used before, and simply divide by 207, and we get a separation between these two nuclei of 357 femtometers. This is already a shorter distance than the sun was for its barrier, which was around 743 femtometers. And this puts our potential energy barrier at 0 at 357 femtometers. So what's that equate to in normal energy? It's about 4,034 EV. So you could think about this as always having 4,034 EV in that case, um, or at least that's how I'm going to represent it. I'm going to subtract this value from it, so our 0 is at 357 femtometers, and then the rest of the function is treated normally. When we take the average, so we integrate our function from 3.5 to 353 or 357 femtometers, we end up with an average barrier height of 0.137 MeV. This is the highest value we've had so far, and that's kind of to be expected because it gets higher towards the left side. You know, the graph peaked towards the closer to the atom. But because the barrier width is much shorter, this is going to actually turn out our probability to tunnel at room temperature, so no extra energy required, is actually 1.3 times 10 to the minus 8, which is 10 orders of magnitude greater probability than at the core of the sun, which is actually insane. And that's where cold fusion came from. They observed this effect back in 1950, back in the 1950s, and it was promised to be the next energy source, and everyone was really excited. But then they ran into a few problems. Like the first problem is muons only last for 2.2 microseconds, which sounds like a really short period of time, but it's actually enough to trigger around 200 fusion interactions because the probability to tunnel is so high. And our value here is probably actually a little low, so this isn't accurate. It's accurate in the sense that it shows the difference between the other three, and it predicts what we were expecting. We were expecting to see fusion to be much more likely here than in the other three cases. But the other problem that happens with muon catalyzed fusion is the muon will get stuck to one of the fused cores. So ideally you want your muon to be free and running around the hydrogen, causing bonds, and then as soon as fusion happens, it goes to find another hydrogen. But unfortunately, it occasionally gets stuck to the helium it produces and then doesn't facilitate any additional fusion events and then decays. So there's a little bit of research being done right now in attempting to liberate those by doing X-ray pulses of the right frequency and energy, basically, to knock the muons free. And that'll increase the amount of fusions per second. But the other big problem is it's really expensive to produce muons right now in terms of energy, because pions are created from busting apart the nuclei of atoms. So you need a really powerful particle accelerator to create pion streams. And then those pions have a small percentage probability of turning into muons, which you can then send downstream. But it's not completely hopeless. There's still research going into it, and maybe someday we'll get cold fusion reactors or something cool like that we hear in sci-fi. So I just wanted to thank anyone who's made it this far. This ran a little bit longer than I was expecting, and it was a lot of fun to work on. I had to shift my focus quite a bit from muon catalyzed fusion, mainly because I frankly just couldn't understand most of the quantum mechanics that was really related. And keep in mind, all of this is a one-dimensional, as simplified as possible case of an application of quantum mechanics. Looking at some of the three-dimensional cases and the three-body problems that arise from it, because normally muon catalyzed fusion or any of these fusion events should be a three-dimensional, three-body problem where you have the electron, two protons, or two protons and a muon. So it can get pretty complicated, but it's very interesting stuff, and I'm planning to look into it some more, and I just wanted to thank everyone for humoring me and watching this video, so thanks.